Good day, folks. This is video number 13 in the playlist that's devoted to motion design application in 3D Experience, where I'm going to be doing a dynamics problem. The title of the video is Oscillating Block under Coulomb Damping. So essentially, I have a block, as you can see there, the green block, which is attached to two supports on the side with springs. And this block is subjected to oscillation. You move it basically and just let it go. It will oscillate back and forth. And if there is no friction, there is no damping, this will oscillate forever. But if there is damping, then the amplitude of the oscillation decreases. And then we're going to be, of course, doing specific damping type, which is Coulomb damping due friction between the block, green block, and the surface that is sliding on. Now it is it is possible to look at this problem that I have here as a single mass and a single spring, but the two stiffnesses, the stiffness of the springs add up because they're in parallel. But that's not how I'm going to do that. I'm going to model it with two springs. Now, uh, this problem actually was done in another playlist that you'll get the information about at the end of the presentation, using the mechanical systems design and mechanical systems experience, which is applications in 3D experience, which is not the same as motion design. Motion design is a cleaned up and integrated version of those two things. This is why I'm doing another set of video segments on specifically motion design. Although many of these problems have been already done in my playlist for 3D mechanical systems design and mechanical systems experience, that's not what this playlist is for. Now, here's the way it's done. First of all, it's assumed that the block is positioned, as you can see, not equally between the two sides, because otherwise there won't be any excitation, there won't be any reason that it oscillate, but it's slightly shifted to the left so that the spring on the left is in compression, and obviously spring on the right is in tension. This is why the block begins to oscillate. Now, the stiffness and the friction coefficient are given. Also, because we're doing Coulomb damping, you have to make sure that there is a normal reaction force on the surface or on the block, and that's why gravity plays a role here. Okay, if there was, for example, no gravity, friction won't do anything because there won't be any reaction force. Now, and keep in mind that because you're assuming that it's the friction that's responsible for the damping, you cannot use viscous damping. Have to use contact condition between the block and the surface. All right, dimensions are given here. But this is not how I'm going to be doing it in this problem. I'm going to repeat this problem in a different way. Uh, we have the block, we have the support. So what I'm going to do is this support is stationary, this base is stationary. So one way to do it is, of course, later on we're going to fix it, but you create a manual marker on the left of the track, a manual marker on the right of the track. This business of marker is extremely important and central to uh, can be central to the motion design application. And then remember these heights and 2 points, one on the right face of the block, the other one on the left face of the block. And we're going to the same height, both of these same height. And then we're going to put springs between them. So what I'm telling you is the shape of that uh, ground, the gray piece is not important. This is how I'm going to do it in motion design. Could I not have done it exactly the way it was done in the other the other playlist where I use mechanical systems experience to do that? Yes, but I'm doing it differently. Now, uh, so when you look at this problem, this is the geometry, and yeah. And by the way, the free spring okay, spring reference. There's an e missing here. Length is 0.5, 0.5. So that one, this is in compression. This is in tension. Now, the other thing is that I can, when I make the parts, I can put this block anywhere I want, but then later on move it to the position using initial conditions in motion design. But I'm not going to do it like that, because if I go that route, the springs don't look nice, and it can be ugly when it when it comes to visual outcome of that problem. Now, here's the playlist that I was talking about. It's this problem that was done in a different playlist, which is called Dynamic Scenario and Animation Modeling, where I'm using mechanical systems experience to do the problem. All right, let's go ahead and do that. So I'm going to start from scratch. So let me get rid of these. Okay, let's start with assembly design. All right, and I'm going to insert the track first. Insert new, insert 3D part. I'm going to call this thing track. Track, and I'll leave it like that, gray. So let me go make it. It's just a box that's 1100 millimeter long. So on that plane, I will sketch. I'll put it like that. Mention these things accordingly. So let me see now. This is the block is 100 millimeter long, so I'll make this thing about 200. And this I'm going to make that it's totally irrelevant. I'll make it 10. Fine. The only thing is that I want to bring this thing and put it on that. This controls that. And I'm going to make it coincident. Right there. Okay. So exit. And I'm going to pad this thing by 1100. What is that? 1100 millimeter. Ooh, oh my God. This should have a millimeter. 1100 millimeter. That's a lot better. Okay, now we're going to insert the block. So insert 3D part. I'm going to call this thing block. And block. Let's go make it. So on that vertical plane, I will sketch. This time it's going to be 100 millimeter by 100 millimeter. Does it have to be symmetric or anything? Not really. So let me select this. 100. And then this. Also 100. Okay, I'll bring it up and put it on that top face. So control that line, and we're going to make it coincident. There, exit, and pad it by 100 millimeter. Yep. I forgot to change the color of it. Let me change this thing to green. Okay. So what I want to do is I want to move this thing. I want to move this face by 400 millimeter, 400 millimeter to the right. Now, also while I'm at it, let me go and create my points here. While I'm in this part block, I'm going to create a point, a center of gravity, and that's this face. So it's going to create a point at the centroid of that face. And I do another one on this side. Same thing. So it created 2 points, one on this face, the other one on that face. Now to move this thing by 400 millimeter, there are different ways of doing it. You can, for example, if you want, you can use a compass. You go all the way to the assembly, bring this thing, put it, for example, on that. Let me let me let me turn this thing around. Actually, let me put it on the side. Okay, and then double click on this arrow, and you want it to go 400, negative 400 along the W direction. There. There are other ways of doing it, please. This is not the only way. So right now, what we know is that this is 400 millimeter, this is 100 millimeter, and this is 600 millimeter. Excellent. All right. Now, we're pretty much done here. So what we're going to do is we're going to go and go to go to motion design as an application. All right, so let me move this thing up here so I can see what's going on. Yep, motion design, and say okay. Let's see what we have here. First of all, there is a gravity of 9.81 down, Z, that's good. We also have several bodies here. We have the track that I made and the block that I made, okay? And there's also this ground. This ground is something that's always created by motion design, and this is fine. Now, a couple of things I'm going to do. By the way, if I double click on this block, double click on the block, it tells you that this rigid object has a mass of 7.77 kilogram, and in fact, it matches the number that I have here, mass of 7 here. See that? Mass of 7.77 kilogram. And the reason is that I didn't specify any material, so what it does, it specifies the default properties of steel, whose density is 7,770 kilogram per meter cube. So this is the correct mass. Now the track, if you double click on it, it also gives you the mass of the track based on density of the steel. But I don't want that thing to move anyway, so I'm going to make it rigid to make my job easier. I don't have to worry about it. If you went to that other playlist where I have done this problem, since there was no provision for rigid massless object there, I had to bring down the mass. Really, the mass of this doesn't matter because it's going to be stationary. It's going to be stationary. This is not going to move anywhere. So whatever the mass is, it really doesn't matter. Okay, let's go back here. Now, the other thing is that every body has a marker. So this is the marker for the ground, global 000 for the assembly. This is the marker for the track, and I need two of them, two more, one 50 millimeter up, the other one 50 millimeter up on this side, and this is uh, the uh, the marker for the block. Okay, fine. So while I'm at it, I'm going to make some markers here. Let me go to mechanism. I'm going to make a marker. Select the body. I'm going to do two marker on this track. So select this. The first one, I'll call it left. Instead of calling it two, I'll call it a manual marker on the left. Just so that I can read it now. It's going to be x of 0 because I'm doing a manual one, x of 0, y of 0, and a height of 50 millimeters. So I'll put a 50 here. Note, oops, 50, and then say OK. Notice that it created a marker up there. And if you want to see it, click on this. You can see that right there, top one. OK. And then I want to do another one, marker. Again, the body is the block, not the track. And I'm going to call this thing right one. And it's going to be also 50 up, but 1100 millimeter along the y, 1100 millimeter along the y direction. So there we are. So we have my two markers. These are the two markers. These are the places where the spring are going to come, going to be constructed. So let me see. See, the spring is created between that marker and this point. I could have used markers, for example, on these faces, but it's okay. You don't need it. So where is the spring? It's a mechanical machine element. There is a spring, axial spring. It's a helical one. And it says between one endpoint, I'm going to use this marker on the left. And the other endpoint, I'm going to use that point that I created on the face that you can see. If I had not moved this thing to the right location, it would have been, as I said, I can use initial condition, but this thing would be really squished. This spring will be squished. Now, free length of it is 175. No. Free length of it was here. The E missing here, 500 millimeter. And the spring constant is 10,000 Newton per meter. That's one. Let's do another one. Another helical spring going between this marker and that point. It's exactly the same story, 500 millimeter and two more zeros, 10,000 Newton meter. There's no viscous damping here. This is viscous damping. We don't have viscous damping. We're going to do Coulomb damping later on. Good. So we have our two springs here, machine elements right there. Good. Now, the nice thing is that you can put your cursor on, you can see it. If this block was too close to the left side, it would be really squished. It would look squished, but then I have to apply, when I apply initial condition, it behaves correctly. Now, the other thing is that I go to mechanism, I have to specify 3D contact between the block and this track. 3D 3D contact between the block and the contact. Okay, and the coefficient contact properties, the coefficient is 0.4. That's what you're told right there, 0.4 friction coefficient for Coulomb damping. Now this thing doesn't come into the picture because there's no impact, so at some time you have to come back and fool around with this stiffness scaling, but that's okay, just leave it the way it is right now. All right, now, uh, okay, we have to fix, notice that when it comes to joints, let's go to joints here, see if we can find it. Joints, yeah, there are no joints here, but I have to fix this track. Okay, the ground is fixed, but not the track. So what I need to do is I go to joint. You see this? See this joint? Fix track. And then we say okay. Very good. And let's go quickly do a preview here. See whether it works the way it's supposed to. Here is the preview right there. Let's give it time. We'll see. Something is definitely not quite right. You may have to work on it. Okay, so let's stop this thing, exit that. And I'm going to run it and also see what's going on. Move this thing there. Okay, so we go to what I'm going to do incidentally while I'm at it, I'm going to create a probe kinematic measurement. And this is going to be, for example, at a point, let's say this, I don't know, this point or that point, it makes no difference. So it really doesn't matter. I'll select that point and then say OK. So it's going to show me the global position of this point that I can plot later on. Okay, so let's go run it. Simulation. Well, how many seconds is that? Let's check it out. Default is 5 seconds. If you want more than 5 seconds, obviously you have to ask for it, but just leave it 5 seconds here for now. Okay, so let's go ahead and run it. Wait until this goes to 100%. Please keep in mind that there are a lot of different ways of doing these problems. This is just one way. And we close it. Let me select the last result, the last line, and go to results. And here's a play animation. Move this thing out of the way for you. And then we play it. See, I don't like the way this is twisting. It's not supposed to, but that's okay. Just leave it the way it is. Let's look at the plot. Let's see what you want here. Kinematic measurement. Okay. Yeah. And then the Y position after the plot. Okay. So I don't particularly like this. So let's find out what's going on here. Let me close this for a second. Okay, I want to make sure that everything is done correctly here. What I'm going to do is, remember that I said may have to go back and change that in the contact, change that stiffness. Let's go here, contact, right there. And let me make this thing 0.1 and run it. But before running it, I also want to change the, well, it's going to be, the graph is going to be jagged, but so one way to fix that is to go to, let me run it and then we're going to do that in a minute. Wait until this thing finishes. Okay, select the result, go to results, animation, and play it. Okay, that looks a lot better for now. Go to 2D plot and select the probe kinematic measurement in the Y direction plotted. This is still jagged here, so what I'm going to do is the following. I will go to dynamic step and expand this thing. Instead of getting the result every 20 set of results in 1 second, let's make it 100. So this records more information. That's why it may take care of the jaggedness. Say okay. And now we're going to run it. Okay, so we go to results, 2D plot, get the kinematic measurement, plot in the Y direction. Okay, we didn't have to go all the way to 4 to I don't know how many seconds I'm going. Let me keep this thing on the side. Don't close it. But let's go ahead and do it instead of over 5 seconds. Let's do it over 2 seconds and run it. And it automatically update this graph. See that? The jaggedness is gone. And this is a linear drop, and that's what Coulomb damping should do. If this was a viscous damping, it would not be linear drop of the amplitude, but it will be an exponential drop. That's a good sign, all right? And in fact, look at those numbers. These between 500 and 700 millimeter are your initial conditions. Remember, we released it when it was 400 millimeter away from that side. And this point was 500 millimeter away. That face was 400 millimeter away plus the length of the cube is going to be 500, etc. So this is the global coordinates. All right, folks. So yeah, that's pretty much it. Good luck.